I will start with a brief presentation. The title of our contribution is Beyond and Across the Iron Curtain, the Rise of Neutrino Astronomy. Neutrino astronomy is based on what is without doubt the strangest of the known elementary particles, capable of traveling billions light years from the most extreme environments in the universe to Earth without interacting with matter, barely interacting. And thus, to follow the tracks of such elusive particles, one needs very unusual detectors. The development of successful neutrino telescopes has required decades of efforts. On the other hand, the very property which makes neutrinos difficult to observe makes observing them interesting and fascinating. The field of neutrino astronomy started in earnest in 1987 with the unexpected detection of a few neutrinos from a supernova in the Large Magellanic Cloud. But the real birth of neutrino astronomy as an established field goes back to November 2013, when the international collaboration that operates the ICECube Neutrino Observatory in the South Pole announced that they had detected the first very high-energy neutrinos coming from outer space. ICECube is a gigantic cubic kilometer-sized detector buried more than a mile deep in the very clear Antarctic ice. It employs strings of light detectors lowered into 2.5 kilometer deep holes drilled in ice and catching the Cherenkov light from the charged particle emerging from neutrino interactions in ice or rock. This very weird telescope is designed to look down through the planet at the northern sky, since the neutrino is the only known particle that can reach IceCube from the northern direction. In 2017, nearly in parallel with the first joint detection of gravitational and electromagnetic radiation from the merging of two neutron stars, observations by IceCube were confirmed by ground and space-based gamma-ray telescopes, providing the first ever identification of a likely source, a blazar actually, of high-energy extragalactic neutrinos and of high-energy cosmic rays that proved the potential of neutrinos in multi-messenger astronomy. These results were actually the culmination of a quest that first fired the imagination of a small group of visionaries about 60, 70 years ago. It has been a long journey indeed. Giulia will now present some aspects of our investigations on the early developments of neutrino astronomy within the context of the interactions between scientists on both sides of the Iron Curtain.
Thank you, Luisa, for the introduction. So as Luisa has already mentioned, in this contribution, we are willing to investigate the rise of a new discipline towards the end of the 50s, the so-called branch of neutrino astronomy, lato sensu. In fact, as we will see, at the beginning of the atmospheric neutrinos, namely secondary particles generated in the interaction of cosmic rays with the atmosphere and solar neutrinos, were sought. The goal is to embed this event of the history of physics into the larger geopolitical framework of the Cold War and to hint at the permeability of the Iron Curtain starting from the years of the Krushchev Thaw, when international scientific cooperations became feasible and started even to be appreciated. We will investigate the role played in this by some renowned conferences, such as the Rochester International Conference on High Energy Physics, ICHEP, and the ICRC, the International Cosmic Ray Conferences, which set the stage for the collaboration that went beyond the national borders, especially nurturing the scientific partnership of scientists from the two superpowers. But let us now start from the beginning by recalling some relevant steps in the dawn of neutrino physics. This elusive particle had first been reluctantly suggested by Wolfgang Pauli in a desperate attempt to prevent the law of energy conservation from being given up. On the 4th of December 1930, Pauli had sent a letter to the Dear Radioactive Ladies and Gentlemen gathered in Tübingen to suggest the existence of this bizarre particle. He said to the astronomer Walter Bade, who was visiting his home in Zurich that day, "I've done a terrible thing today, something which no theoretical physicist should ever do. I have suggested something that can never be verified experimentally." As a matter of fact, the possibility of detecting neutrinos was soon given up by Bethe and Payas. who in 1934 computed the cross-section for the inverse beta decay, finding out a value of 10 to the minus 44 squared centimeters, and concluding that practically there is no possible way of observing the neutrino. However, in 1945-1946, Bruno Pontecorvo, back then one of the leading figures in the construction of the Chalk River reactor in Canada, and he's somebody who will come up later on in our talk again, Bruno Pontecorvo challenged Bethe Payal's opinion and proposed the first radiochemical method for the detection of free neutrinos from a nuclear reactor. This paved the way for the subsequent attempts to observe this neutral elusive particle. In 1953, Rains and Cowan proposed their method to detect free antineutrinos from a reactor by using tanks of water as a detector at the Savannah River nuclear power plant. At the same time, also Raymond Davis, first at the Brookhaven National Laboratories and later at Savannah River as well, planned his experiment to detect antineutrinos based on Pontecorvo's chlorine-argon method, which, however, requires neutrinos. Thus, the result of his experiment showed that the capture rate was much below the rate expected if neutrinos and antineutrinos were identical particles. Finally, in July 1956, the first positive results to prove the existence of reactor neutrinos at the hands this time of Rains and Cowan arrived. After that, the neutrino became an experimental reality, getting an independent identity after having served as useful hypothesis for many years. Speculations regarding further experiments ranged from reactor and accelerator-produced neutrinos to neutrinos generated by cosmic ray interactions in the Earth's atmosphere, and even neutrinos from the Sun or other extraterrestrial sources. It was at that moment, actually even before the actual detection of neutrinos, because this happened in January 1956, that the famous nuclear and cosmic ray astrophysicist Philip Morrison pronounced the following statement: "The neutrino provides in principle a new kind of astronomy. Until now, the only radiations from outer space that we have studied are visible light and microwave radio. The neutrino beam from the sun and stars also comes to us bearing information about the universe, and we shall surely someday read a part of that text." This prediction did not come from him by chance. Since many years, he had been very close to Bruno Rossi, a prominent cosmic ray physicist, and his team at MIT. After the advent of space age in 1957, they had been planning space experiments for the detection of extraterrestrial gamma rays and X-rays. Morrison, who had a firm understanding of the astrophysics of cosmic rays, was able to perceive the neutrino as a cosmic messenger, at least in a vague sense. Another contribution attesting that this way of thinking about the neutrino was already present back then is Rains and Cowan's paper on Nature, titled "The Neutrino," and published on the 1st of September 1956, right after the discovery of the neutrino, where they described the ghostly particles as cosmic and products of all nuclear energy generation processes in the universe. All this was happening in the West. But we need to recall that in the mid-50s, the Krushchev Thaw was beginning to depict more penetrable borders between the US and the USSR, opening up to novel collaborations and exchanges. In 1955, Nikita Khrushchev was preparing to embrace the new Atoms for Peace strategy at the Geneva Summit, which was actually the first conference of the series of the Atoms for Peace conferences, promoting the idea that nuclear energy could be used for peaceful purposes, intended to show that the USSR wanted peaceful cooperation with the West. Another fact that is worth mentioning concerns the Soviet nuclear physicist Igor Kurchatov's visit of the United Kingdom with a Soviet delegation led by Khrushchev himself in April 1956. This was surprising because he was the father of the USSR nuclear bomb. He in fact surprised Western scientists with a lecture at Harwell, which was back then the Great Britain's famous nuclear research center, giving deep insights into the problems of controlled thermonuclear fusion and unveiling research performed in the Soviet Union. Furthermore, in 1957, the USSR became member of the UPOP, the International Union of Pure and Applied Physics, and in 1958, the Nobel Prize for Physics was awarded to three Soviet physicists, namely Tam, Frank, and Cherenkov, for the discovery and interpretation of the Cherenkov effect. In fact, in the Nobel ceremony, it was said that an instrument based on this effect had been designed that was capable of registering the passage of single particles, earning the 3 Soviet physicists the Nobel Prize. We will see later that the importance of this discovery, which was applied by Chudakov starting from 1953 for cosmic ray investigations, and later in his pioneering experiments of ground-based gamma astronomy, and then by Markov&Zheleznik in atmospheric neutrino astronomy. Still in 1958, the Second Atoms for Peace conference in Geneva was effectively marked the unveiling of thermonuclear fusion research for peaceful uses, clarified that the secrecy had led to an overlap of work and findings in different research projects all over the world. In addition to all these events, towards the end of the 50s, the USSR started playing a role also in the international conferences on high-energy physics and cosmic rays, both including actually neutrino physics. Furthermore, in those years, as we mentioned previously, the ground was fertile for the birth of the new field of neutrino astronomy that thus began to be discussed at the aforementioned conferences, such as the 6th ICRC, the International Cosmic Ray Conference in Moscow, and at the 9th Rochester Conference, the ICHEP in Kiev. In fact, in 1959, these 2 prestigious annual events were taking place both in the USSR for the first time. In Kiev, the opening speech of the Rochester Conference was held by Blokhintsev, who was back then the director of the Joint Institute for Nuclear Research in Dubna, who, on behalf of the organizing committee, claimed, "In our time, scientists of various countries understand each other perfectly when they discuss their professional matters. There is far less understanding in social matters. We hope that this conference will provide many favorable opportunities for strengthening mutual understanding and consequently for strengthening the friendship of the peoples and the consolidation of peace all over the world." So here is a picture taken from an article written by a retrospective article written by Maurice Shapiro in 2003, and there are some pictures of this conference held in Moscow in 1959. The next year, the 10th ICHEP, the Rochester Conference, hosted this time in Rochester, in the US, saw the participation of a number of Soviet physicists, among whom the theorist Moisei Markov, at the time head of the Neutrino Physics Laboratory, still at the Joint Institute for Nuclear Research in Dubna, and a colleague of Bruno Pontecorvo, mentioned earlier for his work on the radiochemical method to detect neutrinos, and one of the fathers of neutrino physics. In discussing the various possibilities of neutrino experiments that could investigate fundamental problems in weak interactions, Markov shared with the international audience that was present at the conference the hypothesis that he had been exploring since 1957 with his student Igor Zheleznik of experiments with natural high-energy neutrinos to be detected through an apparatus located in an underground lake or deep in the ocean. This detector was meant to reconstruct the trajectory of charged particles taking advantage of the Cherenkov radiation produced by these particles moving at a relativistic speed. Such technique was being used by Alexander Chudakov of the Lebedev Institute in Moscow with the aim of detecting gamma rays from the Crab Nebula and other astrophysical sources, following a suggestion given by Giuseppe Cocconi, also this time at another ICRC conference in Moscow, which is the one of 1959 that we mentioned already a moment ago. The existence of such high-energy cosmic photons could be an argument in favor of the existence of similar fluxes of high-energy neutrinos from astrophysical sources, a possibility that Zheleznik had specifically investigated in his dissertation. However, the neutrino Markov hinted at in his 1960 contribution were mainly atmospheric neutrinos. In fact, in their paper submitted in January 1961, entitled "On High-Energy Neutrino Physics in Cosmic Rays," Markov and Zheleznik were considering only the neutrino flux originating as a result of the decay of pi mesons in the Earth's atmosphere. In parallel, the US cosmic ray physicist Grayson was foretelling that neutrinos would convey a type of astronomical information quite different from that carried by visible light and radio waves, and proposed a large Cherenkov detector to be located in a mine far underground. Underground experiments began to be suggested, also aimed at detecting atmospheric neutrinos, maybe with the hope to observe by chance also neutrinos from other, more exotic sources. The increase of interest in the search for neutrinos coming from the Earth's atmosphere had been boosted by the detection in 1962 of the muon neutrino. And among these early neutrino astronomy underground projects being planned, one could count, for example, Chudakov's work on the construction of an underground scintillation telescope project to study neutrino components of cosmic rays, in connection with the decision to construct the Neutrino Observatory of the Lebedev Institute of Physics in the Northern Caucasus, that then culminated in the construction of what is known nowadays as the Baksan Neutrino Observatory. Meanwhile, in 1964, Davis and Bakel started to plan the project in the Homestake mine in the US to seek solar neutrinos, and Rains was active in a gold mine in South Africa to search for atmospheric neutrinos, in parallel with another similar project in an Indian gold mine, an India-UK-Japan collaboration. In 1965, both experiments detected for the first time natural neutrinos from atmospheric showers. Due also to studies with beams produced at accelerators, neutrinos were becoming a key to a deeper understanding of fundamental particle physics. And that same 1965, a conference devoted to neutrino physics was organized at CERN, to which Soviet physicists such as Chudakov took part. On the other hand, the ICHEP, so the Rochester Conference 1962, hosted in Geneva, had favored the beginning of a friendship between Rains and Markov, also based on their common interests in neutrino telescopes. Moreover, in summer 1962, while the new observatory in the USSR in Tartu was being built, a tradition of seminars was initiated by Yakov Tseldovich in the nowadays Estonian city. There, Pontecorvo held a speech about the role of neutrinos in astrophysics, where he prefigured the birth of neutrino astrophysics and astronomy, viewing the neutrino as a cosmic messenger able to provide information about the universe. You will see this in detail tomorrow in Stefano Furlan's talk about the Tartus conference. Markov's experimental proposal in 1960 had been welcomed warmly, but it had to wait more than 10 years before turning into a concrete project. In fact, it still concerned only atmospheric neutrinos, which were less interesting for astrophysicists. Only in the 60s, new astrophysical objects were discovered that could be identified as good candidate neutrino sources, together with the supernovae, traditionally considered as a possible source of cosmic rays and neutrinos since the 30s. In 1967, the discovery of pulsars was announced, and then the first speculations about these astrophysical objects as sources and accelerators of all kinds of messengers, high-energy neutrinos, X-rays, and gravitational waves, and so on, started taking shape. This certainly paved the way for planning big investments in the construction of those which would later become the spectacular neutrino telescopes that we still have nowadays. Finally, in the 70s, Markov's and Zheleznik's idea of an underwater neutrino detector based on the Cherenkov effect started to materialize with a preliminary discussion on the concept of a massive water neutrino detector, which Rains named DUMAND, the Deep Underwater Muon and Neutrino Detection Project, to be built in the ocean close to Hawaii. An enormous size, ideally 1 cubic kilometer, was required to observe a minimum of few events per year from the proposed sources. So here is a picture with all the participants in the first phases of the DUMAND project, and you can see that Frederick Rains from the Western Bloc and Alexander Chudakov from the Eastern Bloc from the Soviet Union were both present there, among other important physicists. The first plans were sketched in 1973, once again at a conference, this time the 13th ICRC conference at Denver in the US, which was actually the first ICRC hosted in the US. Because of McCarthyism, two prominent cosmic ray physicists, Powell and Blackett, had been denied the invitation because of their leftist political leanings. At the same time, on that occasion, also Vitaly Ginzburg was prevented by the Soviet authorities from attending the Denver conference. This first international collaboration in neutrino astronomy, which was including the US, the USSR, and Japanese scientists as well, moved forward during the 1970s through a series of workshops, hosted both in Eastern and Western locations, which served as the first major stimulus for astrophysicists to seriously consider the role of neutrinos as cosmic messengers. As testified in recollections of some of the participants, these meetings were characterized by a strong camaraderie, notwithstanding different styles and cultures. However, due to the Soviet invasion of Afghanistan in 1979, the cooperation was interrupted because the US government forbade scientists to collaborate with the Russians if using any US government funds. The Russians built, therefore, their own DUMAND at Lake Baikal in Siberia in collaboration with a group from the East German Institute of High Energy Physics in Zeuthen, led by Christian Spiering. The US DUMAND went ahead for about 15 years before being terminated in 1993, along with the superconducting supercollider. This notwithstanding, the DUMAND concept set the stage for later water projects in the Mediterranean Sea, and in particular for ICECube, built deep in the Antarctic ice, and now for a new generation of neutrino telescopes. Here in this the last slide, you can see the Lake Baikal's neutrino experiment on the right and the ICECube at the South Pole on the left. And with this, I would like to thank you for your attention and ask if you have any questions.
Thank you very much, Giulia and Luisa. There is a question by Christian Spiering. Yeah. Yeah, not a question. First, thank you, Giulia, for this interesting talk. Actually, I did not know about the 56 proposals by Morrison and by Reines and Cowan, so that was really new even for me. 2 or 3 remarks. When Markov and Zheleznik calculated the atmospheric neutrino flux, they of course also had the idea that that could be something for astronomy, but that was not calculable. What was calculable, and they did it at the first, was a flux of atmospheric neutrinos. But by the way, the same was done by Zatsepin and Kuzmin, also from Moscow. Yeah. The other thing, oh no, I forgot what I still wanted to say. Well, but okay, that was one of my remarks. I just forget all the other questions. Let first others comment. Okay, thanks a lot, Christian Spiering. And are there other questions? No, okay, I know the second. The second question was, you said that when they planned DUMAND, they knew that they need cubic kilometer for seeing neutrinos from astrophysical sources, and actually that is under dispute because the only thing which was calculated at that time have been neutrinos which have been generated in these so-called GZK processes. So I have a proton interacting with the microwave radiation, and that gives me also pions and then neutrinos, and that was done by Berezinski and Zatsepin. And that gave a very, very raw estimate that you would expect 1 neutrino per 1 cubic kilometer, but it could be by orders of magnitude, by 1 order of magnitude wrong. And what concerns all other sources, they had no idea. And do you know the review of Arthur Roberts where he writes for DUMAND, for the history of the DUMAND project, where he writes, we have no idea, and so the philosophy was build it as big as you can. Luisa, Giulia, do you want to reply or?
Well, no, yes, thanks, Christian, for these precious remarks. And yes, actually, of course, the visionary question is about the fact that you remarked that they had no real ideas, because only during the 70s, let's say, with the observation of the high energy universe with X-rays and stuff, you began to really evaluate the cosmic sources. And so that it was a long process, and that makes all the story very fascinating, really. And the challenges that everybody had to tackle in order to arrive to the ice cube, let's say.
It's a very long journey.
Yes, but we will have occasion to talk about this more, I hope.
Actually, if I would have known in 1987, when I joined this field, that we have to wait 25 years to get a cubic kilometer, I'm not sure whether I would have joined.
Well, that's a typical problem with large accelerators, that there are people who are doing their PhD, postdoc, and so on, while the accelerator is being built. It's a question of these big devices, which are beginning to be similar to the accelerator processes, building processes, actually, yes. It's a change of culture.
Okay. Sorry, there are the two questions, so maybe we can go, and we cannot receive other questions. So one, it's Alan Watson.
Yes, if I could just follow up on the remark that Christian made about the lack of accuracy of the predictions. This has also been a huge problem in cosmic rays. Really, the only prediction was the one made by Gracians, etc., and Kuzmin in 1966. Christian was very lucky. He only had to wait 25 years to sort out his neutrinos. I spent probably more like 40.
Thanks a lot.
I think, as we can see, it's possibly something that historians of science should look into. How, whether you have a prediction or do not have a prediction, really guides the way in which you do the physics.
Yeah, that's a very important remark, and
yes,
that's a question that historians want to follow up. I think there is one time for the last question, and then by Jaco de Zwart.
Thank you. I'm going to do this like this. Thank you for the very interesting talk and very fascinating topic. And I had a question because the neutrino was one of the earliest particles that were thought to be perhaps the dark matter. Already in 1973, people were thinking about this. And I was thinking about the question in how people were putting limits on neutrino mass or the number density, not from experiments, but by using cosmology. And I know that in 1966, Zeldovich and Gerstein, they wrote a paper on putting indeed limits on the mass of the neutrino using cosmology. But I was wondering whether you know a bit more about this development. So that's, say, the more theoretical way of putting limits on what this neutrino was and how it developed from the 60s and 70s. But maybe it's a very long question, but maybe you can give a hint.
No, the interesting question is that Zeldovich, I think that Zeldovich and other Russian people like Churyakov were really pioneers in thinking in terms of particles and cosmology. And so this is, in my opinion, one of the very early hints of the slow emerging of astroparticle physics. But actually it was, as you said, during the 70s, when you began to have a stronger connection between, through the grand unified theories about cosmologies and particles, in which you began to make different kind of guesses about. And because in the meantime, I mean, in the 70s, early 80s, you didn't still have information about the question of neutrino oscillations, and then so all this was going in parallel, I would say. And maybe Christian has some interesting comment to this.
No, my only comment would be that at least in the 80s, there was still the hope that neutrinos could form dark matter. And for that, they should have a mass of something like 30 or 40 electron volt. And there was an experiment, I think the name was Lyubimov in Moscow. He measured something like 30 electron volt. And then it became clear later that this was wrong. We know today that the limit is, the upper limit today is 1 electron volt. And so that's clear that neutrinos cannot be dark matter.
Thanks, Ivo. All this is very fascinating. Unfortunately, we have